So one last thing I forgot to mention about Raoult's law, it doesn't always work. It's not perfect. I mean, you know, who among us is, right? Oh, I can name at least one person in the room right now, but that's beside the point. If our solvent-solvent interactions are about equal to the solute-solute interactions, which are about equal to the solute-solvent interactions, so if, you know, those three pieces from delta H solution from earlier are about the same, then we are going to get ideal behavior. Raoult's law is going to work well. And there's, you know, you can do a long mathematical proof of this, but I like to stick to just kind of one general takeaway on this. So Raoult's law works, or it works less well, or it doesn't work. But when it works well, our solvent and our solute are going to have matching intermolecular forces. So the more of a match you have, the more ideal the solution is going to behave, which means the better Raoult's law is going to predict its actual vapor pressure. And if you have a mismatch, the stronger that mismatch, the larger the deviation is going to be. And so, for example, if we have, this is rubbing alcohol, 2-propanol and water, they'll dissolve in each other. Again, you can take a stroll down that first aid aisle and verify it for yourself. And they're going to behave pretty ideal because water is a hydrogen bonding machine, and isopropyl alcohol, rubbing alcohol, can hydrogen bond as well. Now, if we compare that to something like acetone, it's a nail polish remover, or that's what it's commonly used for, but it's a, you know, it's a common solvent. If we mix that with water, the two of them will dissolve with each other. Acetone will dissolve in the water. They'll form a solution. But the vapor pressure prediction of Raoult's law is going to be less ideal. Their behavior is going to be less ideal. It's going to be farther from that predicted calculated value because this guy doesn't fully hydrogen bond. It's mostly a dipole interaction. Water is fully hydrogen bonding, so you get a little bit of a mismatch there. So these approximate equalities start to fall apart. And so it just behaves less ideally. So really just lean back on that intermolecular forces stuff from the last chapter for that. The better they match up, the better Raoult's law is going to work from the last video. You can still use it to calculate, but if you're to actually experimentally measure the value in a situation like this, you're going to have a larger experimental difference from the theoretical predicted value than this guy. So what we calculate in reality, you know, there's going to be a larger difference here than here. And, you know, you could solve, you know, a lot of delta H's and look at differences, or you could just keep this general takeaway in mind, which this is what I really lean on with this chapter. So that's the last thing about vapor pressures and solutions. I almost forgot, so I had to make one more video. Sorry about that. Now we're going to get into freezing point depression and boiling point elevations.